We're following the handout on cubic relationships. These have the general form as written. They are polynomials of order 3. The highest power of x is 3. If we had a table of values, the question is, how could we determine if indeed we had a cubic relationship? We already know that the first difference will be linear if it's the first difference will be constant if it's a linear relationship. In this case, clearly isn't constant. So let's look at the second difference. You can see from the numbers that is not constant either. If we work out the third difference, here we can see that it is a constant value. The general rule is that if we have a constant third difference for each unit increase in the value of x, then indeed we have a cubic relationship. The key properties of cubic functions. Firstly, recall that the cube of a positive number is positive, which makes sense, but the cube of a negative number is negative. If a number is raised to a negative power, you will be multiplying by an odd number of negatives, which will result in a negative product. Knowing this, we can say that a cubic must have at least one x-intercept, because at some point the numbers must go to 0 or become negative. But because we have x raised to the power of 3, it's possible to have up to 3 x-intercepts. For y equals x cubed, which is the simplest possible cubic, when x is large positive, y will be large positive. And when x is large negative, y is large negative. Similarly, for y equals negative x cubed, we get the opposite relationship, which you can read there. A cubic will have either no or two turning points. For example, y equals x cubed actually has no turning points. Note also that the parts of the curve that look like parabola are actually not parabola. There's no line of symmetry. These curves are skewed. Alright, here's an example. The main skill to learn is to be able to look at a cubic function and sketch a graph of it. So notice here that one of the brackets is repeated, and that tells us that the intercept that we get will touch the x-axis but not cut it. So the first step is to identify the x-intercepts, which of course is when y equals 0. The equation's written in factor form, so you can see pretty easily, I hope, that when x equals 1, y equals 0, and when x equals negative 2, y equals 0. So firstly, if it's not written in factor form, your best option is to use your class pad to solve for y equals 0, or at least use gsolve to get the intercepts. In coordinate form, the intercepts are shown there. This second intercept, 1, 0, we got that from the bracket that was repeated. And the other thing we can note about this, we know that it only just touches the x-axis, but it's also a turning point. It will either be a local minimum or a local maximum. Step 2, identify the y-intercept, which is when x equals 0. So we substitute in x equals 0, and we get a value of 4. So the point is 0, 4. The third thing we need to do is determine the nature of points around the x-intercepts. So to do this, I would normally start sketching the points we already know. So there's the x-intercepts and the y-intercept. We know that 1, 0 is a turning point, so that tells me the shape of the curve in the first quadrant will look something like that. What we don't know is whether or not the curve in the second quadrant will continue to rise or whether it will start to fall. In other words, we need to think about, is the y-intercept 0, 4 actually a turning point? And to figure that out, we need to investigate a value of x between negative 2 and 0. So let's choose x equals -1, and when we do that, just skip forward, we get a value of y equals 8. So that tells us the curve keeps on rising in that section. What we also look at is what happens when x becomes infinitely large, and we can see that y becomes infinitely large. What's a good way to figure that out? Well, what you can do is substitute x equals 1000 and just put that value into the equation, and you'll realize you're going to get a positive value for y, so y becomes extremely large. And we can also do the same, put in -1000 to see what happens when x goes to a negative infinity, and we see that y will also go to negative infinity. So that means in the first quadrant the curve keeps on rising, and in the third quadrant the curve falls away to infinity as y becomes more and more negative. So putting all that information together gives us the ability to sketch the curve. We haven't worked out the exact turning point here. We're only sketching and approximating. If you want to calculate the turning point, then that would be a job for your class pad. The second example is a little different. This time there's no bracket repeated, but fortunately the equation is still in factor form. Step 1, we find the x-intercepts when y equals 0, and we get these 3 points, just reading them from the equation. Step 2, we find the y-intercept when x equals 0, so we substitute x equals 0, and we get a value of -60. So the y-intercept is 0, -60. Thirdly, once again, we want to look at some points around those intercepts, and also what happens when x approaches infinity and negative infinity. So once again, you could substitute 1000 and see the effect, and -1000 and see the effect of that. And then also, once we've put in our points, the shape of the curve is fairly obvious because it has to cut the axis at those 3 x-intercepts. So the only way it can do that is to have this kind of shape. We know that as x goes to infinity, y goes to negative infinity, so that's falling in quadrant 3. But we don't know what happens at 0, -60. The graph could possibly fall, or it could continue to rise and become more negative. So we test a point between -3 and 0, and I chose -1, which gives a value of y equals -72. So now with confidence we can say that the curve continues to increase beyond 0, -60, and that will give us the general shape of the curve.